to a rock. The slope of the tangent line somewhere has to equal the slope of the secant line. This was the mean value theorem. That was a cool proof, but I'm not going to do it now. Okay. But it turns out that there are some really cool consequences of the mean value theorem that apply to what we want to study today. It's called antiderivatives. So here's my first question for your discussion. I will pause and let you talk to each other about that. Say the good morning to someone first, but then go from there. Share by pressing the page down key. Yes, we have used this fact before. I mean, I don't know. What's a good example? Well, maybe here's a weird example. What if I told you guys, hey, let's talk about sine squared of x plus cosine squared of x. Would you guys be able to find the derivative of that thing? You could? All right, let's try it. How do you find the derivative of that? Well, what's the derivative of sine squared? Almost. Remember that what I really mean is this, right? I don't write those parentheses because I'm a lazy mathematician, but that's what I really mean. And so what rule comes into play here when I'm going to find the derivative? Chain rule, sure. Bing, bing, bong, right? So here we go. Y prime, the derivative, will equal what? 2 sine x
times
cosine x, right? And then what do you get here? You get plus 2 times cosine x to the first power times what? Negative sine of x, right? Of course, some of you might have not thought of that. You might have said right away, well, wait a minute, I know something about sine squared plus cosine squared. That's 1. So really, I was asking you guys to find the derivative of, let me use this different color, y equals 1. Well, what's the derivative of y equals 1? 0. And sure enough, if you simplify this, you do get 0, right? So here's an example where the functions are equal, and so it turns out that the derivatives are equal, right? I mean, that's going to always be true. But maybe less clear is this. If the derivatives of two functions are equal, are the functions also equal? This is what I'm going to come back to in just a second. Okay? I want to go to today's lesson. So section 4.9. The book calls the section antiderivatives. Okay? I'm also going to talk about what's called indefinite integration. Okay? This is a mouthful right now, I realize that. Okay? But I'll explain what I mean by an indefinite integral. Okay? And so here's the very first problem I'm going to give you. Okay? So I'd like you to write it down. That first symbol, that curly Q of a symbol here, when I write this, the way you read that is the integral. The integral. What it means is it means the antiderivative. We're going to go backwards from the process of taking derivatives. Okay? And then I have to give you a function. And so I gave you a function, 2x minus 3x squared. And then I wrote down dx. By the way, what is that? dx. We learned about that. What is it? Okay, yeah. So we used to do the derivative with respect to x. Here we're going to say the antiderivative again with respect to x. That's exactly what it means. Okay? I'm saying that x is the independent variable. And maybe y would be the dependent variable. It doesn't really matter. But here I'm going to go backwards. And so what I'd like you guys to do is I'm going to pause and see if you can come up with the function whose derivative is this function. And you can work together on this for just, maybe we'll give you guys 45 seconds. Ready? Go. Let me give you the answer to this problem right here. Check and see. Did you guys get it? The antiderivative is x squared minus x cubed plus 987,654,321. Right? How do I check? I can check my answer by taking the derivative, right?
Oh, okay.
Right?
Big number.
So what's the derivative? It would be 2x minus 3x squared plus
Any number.
0. Well, Mike says plus any number. Is he right? Yeah. I mean, I guess one thing you should understand right away from this example is that there are infinitely many answers. You guys understand? You know, back to this slide we had on the mean value theorem. If the derivatives of two functions are the same, does that mean the functions are equal? Not necessarily. Right?
It just means they would match up.
Now that's a strong claim Joe's making right here.
They would. Because they would have the same slope at any given point.
Yeah.
So I feel like they would match up, right?
Do you understand what Joe's saying?
Yeah.
He's saying, in a sense, they're parallel. Right. So you guys got x squared minus x cubed. And do I know what that graph looks like? Not exactly. But suppose I gave you guys just the antiderivative of 2x dx. We would write that the answer is x squared. But what Joe is claiming is, okay, you might have this parabola, but maybe you have one that's shifted up, or you have one that's shifted down. And how many are there? There's infinitely many of them, but he claims that for the derivatives to match up, you're just shifting vertically. Do you guys understand that?
Horizontally. All real. Plus k where k is any more.
Yeah, what we're going to end up writing is we're going to write plus c. Plus c, where c can be any constant you want. And we'll say that that is the answer, in a sense, to this problem. This is called, and again, I wrote this on the screen earlier, but this kind of problem is called an indefinite integral. And the word indefinite makes more sense now when you realize there's infinitely many solutions. Okay? But I said that Joe made a strong claim here when he said that all you can do is shift vertically.
Yeah.
How do I know there's not some other way of creating a function that gives you the same derivative? I heard you mention a horizontal shift. The problem with a horizontal shift is that the value of the derivative at any given x value may change if I do that.
Yeah.
Okay? Well, it turns out that if you want to prove Joe's claim, which is what I want to talk about here for just a second, what you need to do is you need to go back to the mean value theorem. And so there's a couple of things we really want to talk about. Here's the first consequence of the mean value theorem. So suppose that the derivative is equal to 0 on an open interval. Then what I can prove is that f has to be constant on a closed interval. Okay? So if f prime is 0 on an open interval, then f is constant on the closed interval. And this is done in your reading for today's section. I'll show you guys that. I don't want to work through the whole thing because it's there. Here. consequence of the mean value theorem. This is the very end of the section last time. If you have a zero derivative, then what does the mean value theorem tell me? Well, see, if the derivative is 0 on the whole interval, I have this equation, right? Here, let's show you how it works. So, we are given that f prime of x is equal to 0 for all x in the open interval a, b. Then the mean value theorem, MVT, tells me there exists a c such that what happens? You guys learned that theorem. What did the mean value theorem say? You guys did the homework, right? F prime of c, that's right, is equal to what? There it is. F of b minus f of a over b minus a. But wait a minute. We just said that f prime of c is equal to what? 0 everywhere. That was the given. Right? So now let's multiply both sides by b minus a, whatever that is. What would my new equation be? 0 is equal to what? F of b minus f of a. Okay?
Oh, yeah, it has to be constant because the only thing that would be is that you have to.
Yeah. I know that f of a equals f of b at this point, and I could do this for any a and b in the interval, and you're fine. And if you kind of look through, it's true for every single pair of points in a given interval. So yeah, you're constant. It's the only way it can happen. Okay? Well, what we get then for free is this following consequence. Functions that have equal derivatives must differ by a constant. And this is really kind of cool what they do. If you just focus on the equation in the proof, they're going to use the fact that f prime and g prime, right? If we say that they equal 0, then the difference equals 0. Well, if the difference equals 0, we just proved that the difference, f minus g, must be a constant. Does that make sense? And so that's exactly what you want. F is equal to g plus a constant. If you follow that, I'm done with theory. And it's time to just practice some antiderivatives. Okay? And so to get better at this, let's try this one next. The antiderivative of the cube root of x squared dx. Now, if I'm giving you a problem like this, kind of like we used to do with derivatives, probably the first thing you want to do is you want to rewrite it. Okay? So how do you think I should rewrite this function? X squared to the 1/3 power, sure. Of course, you could simplify that also. We could simply write x to the what? To the 2/3. Okay. All right. I'm going to pause and let you talk to someone next to you. See if you can come up with the antiderivative, and also check your answer by taking the derivative to see if you got it right. I'll pause for a second here. When I'm given a problem like this, my reasoning is as follows. I first look at the power, and I try and figure out, well, what's that going to become? I know that when I take a derivative, I subtract 1 from the exponent, so I'm going to add 1 to the exponent, and this must be 5/3, right? But that's not the answer.
No, because you really have the.
Yeah, if I took the derivative right now, I would get 5/3 x to the 2/3, right? So what you can do is you can kind of adjust something. Put a number out front. So like if I put the constant 3/5 in front, see that? Now when I take the derivative, I will in fact get x to the 2/3. So this is how I do antiderivatives. Oh, one more thing I need to remember is I need to write plus c. And there is the answer to this problem. Okay? So there's some rewriting that happens. You want to put a value here and then put a number out front. Jordan, do you have a question? No? Okay. All right. So moving on, let's try another example. Get rid of this. I don't need this anymore. This one's a good one to try. I'm going to recommend you guys rewrite it just like you did the last problem. Because the way it is now, it would not be easy for you guys to do. But if you do a little rewriting, I think you'll find it's not hard. So do you guys understand how I want to rewrite this? What would you write next? Yes. We're going to put t squared plus 3t cubed dt. Because it's easy to do, you can do antiderivatives term by term. But we have a problem with a product, right? Kind of like in derivatives. What do you have a product rule if you want to take a derivative of a product? Well, taking an antiderivative of a product is even worse. And I promise you, we won't even touch it until Calc 2. It's called integration by parts. It's an important technique, but we label that Calc 2. All right? So we're going to do this. We're going to simplify it, and now try to take the antiderivative. And this is good practice. I'll shut my mouth and let you guys practice and see if you can come up with it. I know that t squared is going to become t cubed, but what do I have to put out front? 1/3. I know here, let me not think about the 3 for just a minute. Let me just think about the t cubed first. That's going to become t to the 4th. But now what do I have to put out front? Okay, and I had a 3. So if I put a 3/4 here, then when I took the derivative, I would be left with just the 3. Does that make sense to you? Yeah? Garrett? I mean, I guess this equals that, right? The antiderivative is this family of functions, is what you have. Okay? All right, moving on. Oh, yeah, I like doing a trig one once in a while. I think that's smart to do. This one I decided we would integrate with respect to what? Theta. Yeah, I used the Greek letter theta kind of to emphasize, hey, maybe you have an angle for your input. Right? Okay, so let's see if we can do this. Oh, this was theta squared, right? I copied it down wrong. Okay. So what would be the antiderivative of theta squared? No takers.
1/3 theta.
Good. 1/3 theta cubed. Okay? Now, don't get fooled into thinking that the next piece is quite so simple. You see, we have a trig function, right? So it's different. All I've done so far are these little polynomials, really. But this is one that you should actually be able to come up with if you know your derivatives. The way I look at it is, if you know a derivative formula, you know an antiderivative formula. So do you guys know any formulas for you take the derivative of this function and you get secant squared of theta? Well, we got a lot of answers, and the correct one is tangent of theta. The derivative of tangent of theta is what? Secant squared theta. You guys remember me telling you, oh, there's these 6 derivatives you want to know?
Yeah, one of them just
Right, well, it's the tangent. It's the tangent. So here's the answer to this problem. Your book actually does a job where they say, let's separate this section off and kind of show you what's going on here. I mean, I remember when we taught you derivatives, they had a whole separate section of the book just for derivatives of trig functions. Okay? Now they don't do that for antiderivatives. They kind of lump it in with the other stuff. I don't need this. I need this. See? Thinking backward, indefinite integrals. And then they say, what about the indefinite integrals of the trig functions? And they do this example, which is kind of nice. And they say, look, you guys already memorized, by the time you get to this point in the course, these 6 formulas. Is that true? The derivative, well, it's funny because I don't think of it as the derivative of the sine of ax. I just know the formula for the derivative of the sine of x. Derivative of sine is cosine. Now, why do they put a cosine of ax? What rule are they just using? They're using the chain rule.
That'll make that easier to make remember the a.
Yeah, I mean, it kind of depends on your point of view. In my mind, I was just like, let me teach you guys the chain rule really well, and then you basically know these 6 formulas, all right? And so which formula did we just use? We used formula number 3, right, where a is 1. And so they said, so the antiderivative of secant squared ax would be, well, they say all this. The antiderivative of secant squared x is just tangent of x. Okay? It's funny because I feel like the book is making it a little more complicated here than they have to. All right? And yet they're trying to get you guys to be able to do more formulas in a sense. I don't want so many formulas. I want a few simple rules. And as we learn this process of integration, once you learn what's called integration by substitution, you can handle any of this stuff without a problem. So yeah, they do some more examples here. Oh yeah, we're going to do a little bit of differential equations today and some motion problems. That's pretty cool. All right, so which should I do first? Maybe a differential equation. Let's do that. So is there one from the book that was worth? Oh yeah, we could do that. It's funny because they write f prime of x is 2x plus 10. I'm going to write it slightly differently. If they really want to talk about differential equations, okay? So differential equations. If they're going to write f prime of x is equal to 2x plus 10, and I'm fine with that, okay? Well, the way that we usually write it when you actually study differential equations is we use the Leibniz notation. We'll write d, should I use f or y? How about I write, let's suppose this is y. Y equals 2x plus 10. Y prime it would be, right? So I would write dy dx is 2x plus 10. So again, there's the Newton notation, and this is the Leibniz notation. And so what people will then do is they'll write the following. They'll write dy is equal to 2x plus 10 in parentheses dx. This move here is called separating the variables. It's a move that's done in differential equations. With me? Okay. And now, why do we do that? Well, we do it because what we want to do next is we want to take the antiderivative of both sides. So you'll see I'm going to put a little pink curve here and a little pink curve there, which means antiderivative. And these differentials are here. So now we're able to do the problem. Okay? Let me work through it here. Let's work through the right-hand side first. Okay? So can you tell me what the antiderivative would be on the right-hand side? X squared, good.
Plus times
Good. Plus 10x plus
C.
c. So some constant goes there. You with me? Now what about on the right-hand side? We'd put y. Yeah, now, it's funny because you were about to write plus c, but here's a question I have.
You don't, but because the C's on the other side,
Yeah?
it wouldn't really be all, it could be, you could put a different constant.
Right. I mean, is this constant, does it have to be the same as that constant?
No.
No. Matter of fact, let's call this C1 since that's the first constant we found. And I'll put a plus C2 here for now, although I will tell you, never again do I want you to put constants on both sides. Because the very next step, I could get y by itself and just write C over here, right? And what is C? C is equal to whatever C1 was minus whatever C2 was. I subtracted it from both sides. You with me? So if you take the antiderivative of both sides, we'll just write plus C on one of the sides, and then we're okay.
So is C all real or all?
C is some constant. I don't know. It could be any real number, right?
Any real?
Yeah, we're going to keep it real in this class. That's interesting. What you
Oh, but again, the complex.
if you're allowed complex numbers, you're right. I could do more. All right. Now, one more type of problem that your book will actually show you, which is really kind of cool they're introducing this, because this doesn't happen until differential equations usually. It's called an initial, although some schools teach this in Calc 2 also, an initial value problem. Okay? So watch how this works. I might give you the following problem. Suppose I tell you that dy dx is equal to 2x plus 10. And I also tell you, let's say, that y of 0 is equal to 3. All right? The reason this is called an initial value problem is because right here, this is what's called my initial value. I mean, it's funny because I wrote x, but let me do this. Let me change the x's to t's. Because a lot of times the input for a differential equation might be t, where t stands for what?
Time.
Time in some units, maybe seconds, for instance, right? And so I'm thinking that the derivative with respect to time is 2t plus 10. But then you can see why we call this the initial value, because this is when the time is what? 0. I'm saying the position, the y value is 3 at time 0. Okay? And now what happens is, if you have this initial value, what this tells me is we can solve for the constant c. I can actually tell you, see, think of it this way. When you write this, you have a whole bunch of parabolas, right? It's a family of parabolas. X squared plus 10x, that graph is a parabola. This one tells you that it starts at 3. Right. So how do you do this problem? Okay, well, what you do is do the same work we had above until you get to y equals t squared plus 10t plus c. And then we're going to take that initial value, right, and we're going to substitute. Now, if we substitute in, what do we get? Well, y is 3, and t is 0. 0 squared plus 0 plus c. So that tells me that c is equal to 3, which is exactly what Mike just said. We're going to get y is equal to t squared plus 10t plus 3. That's my example of an initial value problem. Oh yeah, you get a tiny bit of differential equations today. And I'd like to use that now and do a little physics with you guys. Are you doing physics? Well, maybe you'll learn. Have you done any formulas in your physics class? My daughter has many formulas in her physics class, and I'm not certain that you really understand where these formulas are coming from until you come to calculus and get to this lesson. All right? So I'm going to write down a formula for you and see if this makes sense. A equals G. Now, what the heck am I talking about? Especially for the... Not everyone in here is taking physics, so let's be nice to them. What does A stand for?
Acceleration.
Acceleration, thank you. And what does G stand for?
Force of gravity.
Oh, yeah. So the force of gravity is what? 9.8.
Per kilogram.
What is it?
Newtons per kilogram.
No.
21 meters per second.
Meters per second squared. I guess if I say the force, now I got to be careful because then I need mass times acceleration. So I want to speak correctly. The acceleration of gravity we call 1g, right? So I know when I go on the Magnum, I hit a couple of g's going around the curve at the bottom, right? So okay, so g. But you're telling me it's 9.8? 9.81? Whatever. I'll just go 9.8 meters per second squared. See, I was raised by an engineer who told me that the acceleration due to gravity was 32 feet per second used to say, per second squared. Okay, so I think of it as feet. But here we go. And this is equal to A of t, right? A of t. The acceleration of an object that's falling is 9.8 meters per second squared. Well, here's something you may have learned. Acceleration is actually a derivative. I taught you that at some point, right? It's the derivative of what? Maybe I didn't teach you that. I tried. Okay. I really wanted you guys to know this, but maybe I'm wrong. It's the derivative of velocity. Right? What is velocity? Velocity would be measured in what units, maybe? Meters per second. So when I say dv dt, that's why it's meters per second squared. All right, so I want to write this equation down. dv dt is 9.8. Okay? So acceleration is telling you, I thought I may have. The rate of change of velocity, that's what's called acceleration, right? I mean, if I'm always going 50 feet per second, that's fine. But if I accelerate, I may go up to 60 feet per second. And the rate of change of that is called, it's the rate of change of my velocity. So now, let's separate the variables. That's that move I just taught you guys about. dv is equal to 9.8. Actually, let's just leave it as g. I don't care what the decimal is so much. dt. dv is equal to g dt. And what am I going to do now after I separate the variables? I'm going to put my little symbol that means to take the antiderivative. So this is interesting. What is the antiderivative of 1? I didn't write the 1. With respect to v? Well, the integral of dv would be v. Does that make sense to you guys? See, I can go from acceleration to velocity by taking an antiderivative. That's kind of what I'm saying. Now, over on this side, g is a constant. Maybe it's 9.8. So let's just write it down again and ignore it. Okay? So what's the antiderivative of g with respect to t? gt. Right? Oh, wait a minute. What do I need to write? Plus what? Plus a constant. So what's this say? This says the velocity at time t you can get by doing gt plus some constant. get that? Now, what's interesting maybe is if you say, here's the problem, guys. I'm going to have a cliff, and I'm going to have a person up here at the top who's going to drop a ball. All right, ready? Go. This could actually be the terminal tower, and there are people underneath that want to catch it. It'd be a good pregame activity.
Doesn't that have enough force going downwards that it would probably break your hand?
You'd want a catcher's glove, yeah. You guys don't know about this? When I was probably about 9 years old, I have distinct memories of this stunt being pulled at our terminal tower downtown Cleveland. And they showed pictures on the news of the baseballs that actually hit car windows and just completely shattered them. So there was this radio contest where these guys had to catch these balls flying. Yeah, it was crazy. So anyways, yeah, you'd want a catcher's glove for sure. Okay, so anyways, what we can say in this kind of a situation is that what is the initial velocity? 0, because he's just dropping it. He's not throwing it. That would change the problem. All right. But if I say that the initial velocity is 0, that's fine, right? So what you'll see if I said the initial velocity is, 10 or something, then it changes the problem. You could be throwing it up 10 or down 10, okay? But in general, what we do is we solve for that constant by plugging in a 0. And so this becomes 0. And what we will write in the physics books is we will write this. Have you ever seen that symbol? V naught. It means, it's the German, naught is the German for 0. It just means the initial velocity. So that's what that constant is. So this constant is the initial velocity. Cool. So what's my function so far? My function is v of t, if you want, is equal to gt plus v initial. And so sometimes you'll see that formula. Okay? All right, but what is velocity? It's also a derivative. It's a derivative of what? It's the derivative of your position function. And in the physics world, we like to use s for that, I think. Am I right? They might use h also. So ds dt is equal to gt plus v initial. So ds is equal to, what move am I doing here, guys? This is called? Good. We're going to separate the variables. We're having so much fun. Let's do this again. All right. Let's see if you guys can write down what we get next. I'll pause for just a second. So I get S equals. All right. What's going to be the antiderivative of gt? Well, remember what the variable is. The variable's t. G is a constant. So the t is going to become a t squared. But what do I have to put out front? A 1/2. And so you'll get 1/2 gt squared. That might seem familiar to some physics people, okay? Plus, well, that was a constant v naught, and so I'll write v naught t. Does that make sense? Plus some constant. Okay? And remember, this is s of t is equal to 1/2 gt squared plus v initial t plus that constant. And so I can write in s of 0 is equal to 0 plus 0 plus c. In other words, this constant is equal not to the initial velocity, but it's equal to the initial, position, right? S naught we'll call it. And so your physics book very well may have this formula S is equal to 1/2 gt squared plus v initial t plus s initial. You might replace that g with an a just for acceleration, but that's going to be one from the book. Some of these other ones are also. And they're really coming from taking antiderivatives of things that you know. So maybe that's kind of cool. Tonight, for homework, yeah, they do give you one section of these motion problems where they talk about some of this stuff. Motion with gravity, we did one like this before. Okay. 40 minutes.